तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture, we saw the two methods to solve the transportation problem optimally, which were the stepping stone method and the modified distribution method. Now, we look at all these aspects of the transportation problem, which is the optimality of the MODI method, economic interpretation of the dual to the transportation problem, comparison among the various starting solutions, how to solve unbalanced problems, and how we ensure that we get integer solutions to the transportation problem even if we solve it as a LP. We will look at all these dimensions one after another. First, let us look at how the MODI method gives the optimal solution. To do that, we first write down the dual of the transportation problem. The primal of the transportation problem is to minimize double sigma Cij Xij. Let us write the primal constraints with specific reference to the example that we are looking at. Now there are three supply points. So as if the first supply point is concerned, x11 plus x12 plus x13 plus x14 less than or equal to a1 or 40. As far as the second one is concerned, x21 plus x22 plus x23 plus x24 less than or equal to a2, and third one would x31 plus x32 plus x33 plus x34 less than or equal to 50. As far as the requirements are concerned, first requirement point will be x11 plus x21 plus x31. This is the quantity received from supply points 1, 2 and 3 respectively. This should be greater than or equal to 20. x12 plus x22 plus x32 greater than or equal to 30. x13 plus x23 plus x33 greater than or equal to 50, and x14 plus x24 plus x34 greater than or equal to 50. We have xij greater than or equal to 0. Now because we are solving a balanced transportation problem, all these inequalities now become equations. So we have all equal to this, and we have sigma ai equal to sigma bj. Now let us write the dual to this problem. Now we introduce dual variables u1, u2, u3 corresponding to the 3 supply points, and 4 dual variables v1, v2, v3 and v4 corresponding to the 4 demand points. So the dual will, since the primal is a minimization problem, the dual is a maximization problem, and dual is given by maximize sigma ai ui 40 u1 plus 60 y2 plus 50 y3 plus sigma bj vj 20 v1 plus 30 v2 vj. Now we realize that every xij, for example x11 is in 2 constraints corresponding to u1 and v1. If we take x2 3, it is in 2 constraints corresponding to u2 and v3. So each xij appears exactly in 2 constraints. So for a corresponding xij, you will have ui plus vj is less than or equal to Cij from the objective function. So for example, we will have as many dual constraints as the number of primal variables. We have 12 primal variables, so we will have 12 dual constraints, which will be u1 plus v1 less than or equal to c11, u1 plus v2 less than or equal to c12, and so on. We will have 12 constraints corresponding to the 12 primal decision variables, and we will have as many dual variables as the number of primal constraints. We have 3 dual variables for the 3 supply constraints and 4 dual variables for these 4. Now these ui's and vj's are unrestricted because all the primal constraints are equations. We have already seen that corresponding to an equation, the dual variable will be unrestricted in sign. So ui's and vj's are unrestricted in sign. So this is the dual of the transportation problem. Now let us see how this dual helps us to understand the optimality of the MODI method. Now let us go back and look at the same problem that we saw in the earlier lecture, and we represent the optimal solution here and the corresponding values of ui and vj as we computed in the last lecture. So if we take this situation, now we find corresponding to this allocation here, we fix u1 equal to 0 to get v1 equal to 4, v2 equal to 6 would give us u3 equal to 1, which would give us v3 equal to 5, from which we get u2 equal to 1 and we get v4 equal to 6. So the u's and the v's are put here. Now what we have done by introducing these u's and v's is that we are trying to evaluate a corresponding dual solution. Now these u's and v's represent the corresponding dual solution corresponding to the primal solution given by these variables. Now the next thing we do here is to calculate Cij minus ui plus vj, and 0 plus 5 is 5, so we get a 3 here, we get 2 here, we get 1 here, we get 1 here, we get a 0 here, and we get a 1 here. So we have calculated Cij minus ui plus vj. Now let us look at this. These represent the dual variables corresponding to the primal basic feasible solution, which is here. So those are the dual variables ui's and vj's. Now how do we calculate the dual variables? Now wherever the primal xij is basic, we define ui and vj such that ui plus vj equal to Cij. Now for this, because x11 is basic, we make sure that u1 plus v1 is equal to C11. If we go back to the dual constraint, it is actually u1 plus v1 should to be less than or equal to C11. So now when xij is basic, we find out ui and vj such that ui plus vj equal to Cij, indicating that the corresponding slack is 0, which means wherever a variable is basic, you find u and v such that the corresponding slack is 0, which means we are satisfying complementary slackness conditions. Complementary slackness condition says that if a primal x is basic, then the corresponding dual slack is 0. So we compute the dual variables in such a way that complementary slackness conditions are satisfied. So wherever xij is basic, we have ui plus vj equal to Cij, indicating that the slack is 0, satisfying the complementary slackness conditions. Now wherever it is non-basic, wherever xij is non-basic, we try to find out the value of Cij minus ui plus vj. For example, if we write the dual constraint as ui plus vj plus hij equal to 0, now wherever xij is basic, we make sure that Hij is 0 because Ui plus Vj equal to Cij. Wherever Xij is non-basic, we try to evaluate Cij minus Ui plus Vj for that, which means we are trying to evaluate Hij, the dual slack corresponding to this constraint, or we are checking whether that constraint is feasible. Now, if all Hij's are greater than or equal to 0, it means the Ui's and the Vj's are such that all the dual constraints are satisfied. If even one Hij is negative, it means that particular dual constraint is violated and the dual is infeasible. Dual infeasibility implies primal optimality, so you enter that variable and proceed towards the optimal solution. Now, when all Hij's are greater than or equal to 0, which is the optimum, it means all dual constraints are satisfied. So, your Ui's and Vj's are such that all the dual constraints are satisfied. Now, Ui's and Vj's are unrestricted in sign, so we need not worry about some of these taking even negative values. So far, we did not encounter a situation where a Ui or a Vj took a negative value, but you can have situations where these can take negative values, and that is acceptable because your Ui's and Vj's are unrestricted in sign. In fact, that is precisely the reason why we solve a balanced transportation problem. A balanced transportation problem has equations, and therefore we have Ui's and Vj's unrestricted in sign. So we need not worry about the sign of the Ui's and Vj's as we compute them. Even if they are unrestricted in sign, it does not matter to us. Therefore, we are comfortable solving balanced problems because we need not worry about Ui's and Vj's having to take strictly non-negative values and so on. They can take any value. Therefore, the moment Ui's and Vj's are such that all the Hij's are greater than or equal to 0, which means all the dual constraints are satisfied, then corresponding to this primal basic feasible solution, we have identified a dual solution which is also feasible. And complementary slackness conditions are satisfied because wherever Xij is basic, we have Hij equal to 0. So we have three things. We started with a basic feasible solution to the primal, we applied complementary slackness and found out a corresponding dual, and we verified whether the dual is feasible, and if the dual is feasible, it has to be optimal, because that is exactly the way the simplex algorithm works. You start with a basic feasible solution, you apply complementary slackness and find out a corresponding dual. When the dual is feasible, you have reached the optimal solution to both primal and dual. Therefore, the MODI method is optimal. So based on this discussion, the MODI method is optimal, and we have already seen that the stepping stone method is exactly the same as the MODI method. So whatever we evaluate as a net gain or a net loss by putting a +1 in a non-basic position, completing the loop and getting the net increase is the same as finding Cj minus Zj or Cij minus Ui plus Vj. So when Cij minus Ui plus Vj is negative, it means it is profitable to enter this into the basis, if we look at it from the MODI point of view, or it is profitable to put something here and then adjust the allocations as we do in the stepping stone method. So stepping stone method is the same as the MODI method as far as the results are concerned. Therefore, both MODI method as well as the stepping stone method are optimal. Now we move to the next part, which is the economic interpretation of the dual variable. Now in the linear programming, we gave an economic interpretation of the dual as the marginal value of the resource at the optimum. Now let us see what kind of an interpretation we have for these Ui's and Vj's. Now this Xij represents, for example, this 20 represents the quantity transported from the first supply point to the first destination point. Now what exactly are these zeros and 4s? Now let us look at a situation. The primal of the transportation problem is concerned about transporting the 40, 60 and 50 available in the 3 supply positions to meet the 20, 30, 50 and 50, which are the demands of the 4 demand points. Now one way of looking at it is we solve the primal to find out exactly how much to transport from every I to every j, and we get an optimal solution 20, 20, 10, 50, 40, 10 respectively. If on the other hand, let us look at the problem in a different way. Now there are some supply points and there are people who have these 40, 60 and 50 as well as people who need these 20, 30, 50 and 50. Rather than directly transporting it, let us assume that there is a third party person who is interested in buying all these things from the supply points, from the suppliers, and then who is interested in selling these to the demand points. So let us assume that there is a middleman or a third party person who is willing to buy these 40, 60 and 50 exactly at the supply points, and then he is going to sell these 20, 30, 50, 50 back to the people who are interested in buying at the demand points. In such a situation, the UIs will represent the value, the money that the person will be willing to buy, and Vj's will represent the amount for which he will be willing to sell it at the destination points. Or for example, if the middle person is going to buy one from here and sell, for example, to here, then the difference should be, the difference between the buying price and the selling price should be equal to the cost of transporting, which is 6. So the dual variables are interpreted as the marginal worth of the commodity at the supply points and the marginal worth of the commodities at the destination points when it comes to buying and selling respectively. Now it is also obvious that we were actually not interested in finding the absolute values of the u's and v's, but we are finding out the relative values of the u's and v's by fixing u1 equal to 0 always. For example, if we had fixed u1 to some other number, then the u's and the v's will get adjusted, and that is acceptable to us because ui's and vj's are unrestricted in sign. It is also important that we are not interested in the absolute values, we are only interested in the relative value. For example, if this is going to be a basic variable at the optimum, then no matter what price the person is going to pay and buy here, it is necessary for the person to sell it at 6, if this is rupees, at 6 rupees more to this person, so that both are able to optimize. Otherwise, if the third party person is willing to sell for something less than 6, then the person will lose, and if the person is willing to sell for more than 6, then this person will not be ready to buy from this person. So the competitive market will ensure that this ui plus vj will be equal to Cij, where ui and vj are interpreted suitably as buying and selling respectively. So this is the economic interpretation of the dual variable. The dual variables can also be unrestricted in sign, it does not matter, it is only the relative difference that matters and not the absolute value. So they can be unrestricted in sign. So some of them can take positive values, some of them can take negative values as well. Now let us also look at the third dimension. We said there are two basic steps in solving the transportation problem. One is to identify a basic feasible solution, and second is to get the optimum from the basic feasible solution. So when we identify the basic feasible solution, we looked at 3 methods: the northwest corner rule, the minimum cost method, and the Vogel's approximation method. Let us look at some aspects of these. So we could get started using the northwest corner rule or the min cost method or the Vogel's approximation method, and we could get the optimal solution using the stepping stone method or the modified distribution method. Now when we looked at the 3, northwest corner rule, minimum cost and Vogel's, we realized that northwest corner rule is the simplest of them. All the 3 of them give basic feasible solutions. All 3 of them will not give solutions with the loop, because every time an allocation is made, they allocate the maximum possible, which is the minimum between the supply and the demand. Now among the 3, we realize that the northwest corner rule is the fastest in terms of implementation. It is quicker, but it does not guarantee a good solution because it does not use cost information while making the allocation. The minimum cost method is expected to give a value better than the northwest corner rule, lesser than the northwest corner rule, because it takes into account the cost while making the allocation, and the Vogels is expected to perform better than the minimum cost because it goes to one more level of detail in computing the penalty associated with not allocating at the minimum cost cell. In terms of computational requirement, Vogels takes more time compared to the other two. Since this method gives a superior starting basic feasible solution, it is expected to take less number of iterations to reach the optimum. It is also advisable that the starting solution is generated using these methods because they guarantee basic feasible solutions and they do not get into any loop. It is not absolutely necessary that we should use any 3. We could start with any arbitrary feasible solution. We need to check whether it is basic feasible. We need to look at the number of allocations. If there is already a loop existing, we need to break it and then we need to bring it into m plus n minus 1. If there is a loop, the loop must be broken to get a basic feasible solution. In summary, Vogel's approximation is used normally. Even though it takes a little longer in terms of computation, it is expected to give a good quality basic feasible solution from which we can reach the optimum in fewer iterations. Now, between the MODI method and the stepping stone method, let us look at it again. Now, let us look at the same problem and let us compare what we did when we use the stepping stone and when we use the MODI. Now, when we use the stepping stone, this problem has 6 non-basic positions, and in the stepping stone method we calculated the net gain or loss by putting in each one of these 6 positions. Now, each one involved computing a loop, whereas in the MODI we did not do that. We calculated UIs and VJs using some properties, and then having identified the entering variable, we then computed one loop. So, for small sized problems where the number of non-basic variables are small, stepping stone could be used, but as the problem becomes larger when there are more non-basic variables, because as the problem becomes large, we have actually m into n positions, out of which m plus n minus 1 are basic. So, mn minus m plus n minus 1 non-basic positions exist. As m and n increase, we realize that this quantity will become large. Therefore, it is advisable to use the MODI method or the UV method. Even though the MODI and the stepping stone are essentially the same, they give the same answer, stepping stone's computational requirement will be higher as the problem size increases. Therefore, it is advisable to use the modified distribution method to solve. So, in general, it is advisable to start with the Vogel's approximation method or the penalty cost method to get a starting basic feasible solution, and then approach the optimality using the UV or the MODI method. Now, let us look at one more dimension, which is how to solve unbalanced transportation problem. So far, when we started the formulation, we formulated all the supply constraints as less than or equal to constraints, all the demand constraints as greater than or equal to constraints, and we formulated an unbalanced problem. And then we put or we added an additional restriction that sigma ai equal to sigma bj, and we converted it into a balanced problem and solved a balanced problem. Much later, when we looked at the dual, we realized that the balanced problem is advantageous because the dual variables are unrestricted. The unbalanced problem would restrict the UIs and the VJs. So, we did not solve the unbalanced problem. So, now the normal if the given transportation problem is not balanced, then how do we solve? So, we need to find out a way by which we are able to convert every unbalanced transportation problem into a balanced transportation problem. We see that through examples now. Now, let us look at a transportation problem given here. Now, let us look at this transportation problem given here. Now, this problem has 3 supply points and 4 destination points. the supplies are 30, 60 and 50 respectively, the requirements are 20, 30, 50 and 50 respectively. Now the supply sum is 140 whereas the requirement is 150. So we clearly have a transportation problem which is unbalanced. Sigma Ai is 140, sigma Bj is 150, so we have an unbalanced transportation problem. So what do we do here? Now to make the problem balanced, we add another supply or another row with the 10 here, so that we are able to balance this to 150. Now we have added another row, we have created a fourth row with the balance quantity of 10 and we have made it 150. Now the cost coefficients remain as they are, but this row that we have added is called a dummy row. This row does not exist in the problem, so it is called a dummy row, and this row is added with a very specific purpose of converting an unbalanced problem into a balanced problem. The cost coefficient corresponding to the dummy is 0. Now we can solve the present balanced transportation problem and get the optimal. Whatever allocation comes out of these 10, however, will not be allocated at all, because we actually have only 140. So somewhere 10 out of the 150 will not be met. Now whichever of these 4 get something from these 10, they effectively do not get anything, because this 10 does not exist. In an unbalanced problem, when the demand is greater than the supply, after we solve a balanced problem, we realize that we cannot entirely meet all the demand. A part of the demand will certainly be unfulfilled. Dummy will act as a virtual supply point with a non-existent 10 and has 0 cost of transportation from the real demand points. Now we can look at another transportation problem which is given here. Now again we have 3 supply points, 4 destination points. The 3 supplies are 40, 60 and 50 respectively. The requirements are 20, 30, 50 and 30 respectively. Now total supply is 150, total demand is 130. So we have again another kind of an unbalanced transportation problem. Here total demand is less than the total supply, or total supply is more than the total demand. Now we convert it to a balanced problem by adding a new column or a new demand point, a dummy with value 20, such that the total demand now becomes 150. So now total demand is equal to total supply, the dummy has cost equal to 0, and whichever supply, we solve the balanced transportation problem. So finally whichever supply point gives to this 20, one or more, to that extent that many supplies will not be taken from those supply points. Now whichever supply point allots to the dummy finally will have that many units not supplied at all. And in this case, since total supply exceeds total demand, we will be able to meet the entire demand from the existing supply. Now by definition, this dummy is a non-existent or a virtual demand point which is created to balance this problem with a non-existent 20 demand and a 0 cost of transportation from the real supply points. So this is how we convert every unbalanced transportation problem into a balanced transportation problem. So every unbalanced problem can be converted to a balanced problem by either adding a dummy row or a dummy column, depending on whichever is necessary. Always the dummies will have cost equal to 0. If we have a situation where the total supply is greater than the total demand, then we have a dummy column, and if the total demand is greater than the total supply, we have a dummy row. If the total demand is greater than the total supply, then in the end we will have certain amount of demand unmet or unfulfilled. However, this way of converting every unbalanced problem to a balanced problem is easy for us, and we can solve every unbalanced transportation problem very comfortably using this. The last and some other aspects of the transportation problem we need to look at. Now there are some aspects to it. The first one is this: unless otherwise stated, transportation problem is a minimization problem. For example, unless otherwise stated, we are always trying to minimize the cost of transportation. This 4 would mean the unit cost of transporting from this point to this point, and the objective function is to minimize the total cost of transportation. However, there could be situations where we can have a maximization transportation problem. The common rule that is followed is to convert the maximization problem into a minimization problem by multiplying the objective function coefficient with a -1. So, if we were solving a maximization objective, then we would have all these negatives, and then we can straight away use either the northwest corner or the Vogel's approximation to get a basic feasible solution. It's the common practice, like in linear programming, is to convert the objective function, in this case to a standard minimization, by multiplying with a -1. We do not try to modify the rules of minimum cost, Vogel's and MODI, which is not desirable. Easier thing to do is to change the objective function into maximization by multiplying with the -1. For example, we do not keep this as maximization and then go back and redefine the penalties by saying penalty will be the difference between the second largest and the largest, and so on. We do not do that. We simply multiply the objective function with a -1, convert it to a minimization problem, and solve as we are used to. If the supply point cannot or should not supply to a demand column, then we assign a big M. Considering a minimization problem, we assign a big M as in simplex for a minimization objective. Once again, since M is large, positive and tends to infinity, M plus or minus any constant is equal to M, so there will not be an allocation. For example, if we say in the same problem that we cannot supply from supplier 3 to destination 3, then this 8 will be replaced by a big M. Now, big M as in simplex is large and positive, and because it is very large, it will not attract an allocation. We are solving a minimization problem. We could also have different kinds of situations that have to be modeled. For example, if we have an unbalanced problem, say here, if we have an unbalanced problem, say this problem is unbalanced because total supply is 150, total requirement is 120. Now, this we call as say demand point 2. Now, this assumes that we need exactly 30 units in the demand point 2. Suppose we say that this person is ready to take any excess that is also possible, then we can do another thing. Now, for example, we can convert, this is a unbalanced problem, so we can convert it into a balanced problem by adding another dummy which has 30. Now, this person is also ready to take the extra 30. It is not necessary that this person should be given 60, but this person is willing to take 30 or anything more. So, what we do is we add another, this is the usual dummy that is added to convert it into a balanced problem. We add another one called D2 dash, who also bids for the extra 30, and now we get 40, 60 and 50. Now, because this is D2 dash, we retain the same costs 6, 8 and 7. This is dummy which has 0, 0 and 0. Now, the other thing we need to make sure is that now this once again becomes unbalanced because 50, 100, 180 versus 150. So, we add another row to balance it with another 30 dummy, but we have to make sure that this person gets exactly 30 or more. Therefore, this will be made as a big M. So, this person will get exactly 30 out of the 150 that is available, and whatever extra that comes into this person will also be given as additional from this person. So, this way we can model other slightly more complex situations in the transportation problem. It is not that we will have, usually in all transportation problems we will have, in a normal transportation problem we will have something like this, where these requirements are firm and these supplies are firm. But it is also possible to model situations saying that, for example, demand D2, if it is an unbalanced situation, then this person can say I would like to take 30 or more or up to 50. So, if the person says I would like to take definitely 30 and up to 50, then this 30 will be a column, the remaining will be here, and then there will be a dummy. Now, to ensure that this person takes exactly 30, this dummy will have to put a big M, so that this 30 comes from the available supply, and anything else that comes into the other dummy this person will take. So, like this it is also possible to model other slightly different or difficult requirements as a transportation problem and solve it as a resultant balanced transportation problem. The last aspect that we have to look at is these integer solutions to transportation. Now, the transportation problem is a linear programming problem. We have seen the primal is to minimize Cij, Xij, greater than or equal to 0. This is a linear programming problem, but then in all our problems that we solved, when we had integer values for the supply and the demand points, we always had integer valued solutions. We never had a situation where we got fractional values. Whereas in linear programming problems, when you have integer values for your right hand sides, one could get into situations where we could have the Xij's taking non-integer or continuous values. In transportation problem, we will not have that situation. If the Ai's and the Bj's are all integer values, then the Xij's will always be integers. That is also because of the way we have made the allocation. Essentially, in all the three, Northwest Corner, minimum cost and Vogel's, we allocated integer values if the supplies and demands were integers, and then we simply added and subtracted integers. So, we were getting only integer values. Now, there is a slightly different way of looking at this integer. After all, in any linear programming, what we are trying to do is we are trying to solve something like this, bxb equal to small b. If this entire thing is written as a vector, then this is vector b, the right hand side is vector b. So, we have bxb equal to small b, and you have xb equal to b inverse b, which is a familiar equation that we have. Now, if this is integer valued, because we have seen that the supplies and demands are integers, so this is integer valued. Now, xb will be integer if b inverse is integer. Now, b inverse is cofactor or adjoint b by determinant b. Now, if this B matrix is made up of integers, then adjoint B will be integers, because every cofactor will be an integer. Adjoint is a transpose of the cofactor, so adjoint B will also be an integer. Now, if xb has to be an integer, then this determinant B should be plus or minus 1. If determinant B is plus or minus 1, then adjoint B by determinant B will still be an integer matrix. B inverse will be integer, B inverse B will also be integer, because this is integer. So, we have to check whether this B is such that determinant B is plus or minus 1. Now, if we go back to the transportation and write it in the form Ax equal to B, where A is the matrix and B is a vector, then this A is made up of 1s and 0s. If you look at this is all 1s and 0s. The coefficient is either 1 or 0. Now, from these coefficients we can find out this A matrix is such that every basis B that we can draw from A, after all this basis is pulled out from the coefficient matrix A, So for every basis B that we pull out from A, determinant B is plus or minus 1, or we can show that this A matrix is unimodular, and because this A matrix is unimodular, every B will have determinant B equal to plus or minus 1, and therefore xb will be integer valued. So xb will be integer valued. If ai's and bj's are integers, then xb will be integer. So if the supply and demand points are integers, then every solution here will be integer. Now going back to the balanced transportation problem, the problem has m into n variables and m plus n constraints like this, and we also have in a balanced problem sigma ai equal to sigma bj. So if we take these constraints and simply add them vertically, we will get sigma a equal to sigma bj, which is this. Therefore the m plus n constraints actually represent a linearly dependent system. Now the transportation problem therefore will be a degenerate linear programming problem because of this sigma ai equal to sigma bj. And because of the linear dependency, we realize that we actually have only m plus n minus 1 independent variables for the transportation problem, and that is why in this transportation table we have exactly m plus n minus 1 basic variables, 1, 2, 3, 4, 5 and 6. M plus n minus 1 is 4 plus 3 or 3 plus 4 minus 1, which is 6. We should remember that even though the transportation problem is a linear programming problem, the balanced transportation problem, because of these equations and because sigma a equal to sigma bj, gives us a linearly dependent system and a degenerate linear programming problem, and we will have only m plus n minus 1 independent variables which will be there at the optimum. However, we do not solve this by the direct application of the simplex, we solve it by an algorithm which is very similar to the simplex, starting with a good basic feasible solution and then moving towards the optimal solution. We solve the balance problem because of the fact that these equations give rise to unrestricted ui's and vj's, which make it very easy for us to look at this problem through the MODI method. And when we use the MODI method, we do not have to worry about some of these becoming negative, simply because it is fine with us, ui's and vj's are unrestricted in sign. So this is about the integer solutions of the transportation problem. So in general, we have looked at the various aspects of the transportation problem, and we have seen 3 important ways to solve the transportation problem to get the basic feasible solution using the northwest corner rule, minimum cost method or Vogel's approximation method, and we said Vogel's approximation method is more desirable compared to the other 2. We saw 2 methods to get to the optimal solution, the stepping stone method and the MODI method, and we said the MODI is useful for solving large sized problems. We also saw examples of how to solve a transportation problem which is degenerate by itself. We later saw that the transportation problem itself is a degenerate LP, and then we could get into situations where we have degenerate transportation problem. The degenerate nature of the LP gives us m plus n minus 1, 6 linearly independent variables, but a degenerate transportation problem has 1 less, and we had 5 allocations, which was a degenerate transportation problem. And then we looked at these various aspects of it. How is the MODI method optimal? We looked at the economic interpretation of the duals. We made a comparison among the 3 starting solutions and the 2 optimal seeking solutions. We also looked at a way to convert every unbalanced problem to a balanced problem and to solve. And then we also said that the transportation problem, if the supply points and the destination point or the destination requirements are integers, then we also said that the transportation problem will give integer valued solutions at the optimum. So we used special algorithms to solve the transportation problem because of the very nature of the problem, the nature by which we could get good starting solutions, good basic feasible solutions, and then move towards the optimum. In simplex we normally do not worry about the goodness of the starting basic feasible solution. We were interested in getting a basic feasible solution and we move towards the optimal. Because of the special nature of the transportation problem where good basic feasible solutions can be obtained, we followed an algorithm which started with a very good basic feasible solution with the Vogel's approximation method and then proceeded towards the optimal solution using the MODI or the stepping stone method. So transportation problems certainly used special algorithms compared to the simplex. However, we should also, one last observation we should look at is the transportation problem, the algorithm that we saw, particularly the MODI method, it does exactly what simplex would do. It starts with a basic feasible solution like what simplex would do, and then the complementary slackness conditions are satisfied, it evaluates a corresponding dual, and if that dual is feasible then it becomes optimal. So the transportation algorithm is also an example of a primal algorithm. Remember that we saw some example of, we saw what a primal algorithm is and what a dual algorithm is. A primal algorithm is one which will start with a basic feasible solution, establish the complementary slackness, evaluate the corresponding dual, and if the dual is feasible then it will give optimal to both primal and dual, which is exactly what this algorithm does. We evaluated the dual at every stage after satisfying the complementary slackness, and then when the dual is feasible, which means when all the Hij's or Cij minus ui plus Vj is greater than or equal to 0, we got the optimum. So like simplex, the transportation algorithm is also an example of a primal algorithm. Dual simplex is an example of a dual algorithm. So with this we come to the end of our treatment of the transportation problem, and then we move into another important problem in linear programming which is called the assignment problem. Now we look at the assignment problem next in our Now let us consider this assignment problem using a small example. Now the example is as follows. Now let us consider a 4 by 4 problem. Now let us assume that there are 4 jobs which we call J1, J2, J3 and J4 that have to be performed, and let us assume that there are 4 people whom we call 1, 2, 3, 4 who can do these jobs. The assumption is every person here can do every one of these jobs. For example, this person can do job 1, 2, 3, 4 and so on. Now what is inside this matrix is the amount or the charge or the cost it takes if this person does this job. For example, this person is going to charge 5 rupees to do this job, he is going to charge 8 rupees to do this job, he is going to charge 6 to do J3 and 3 to do J4. Second person would charge 9 rupees to do J1, she might charge 7 rupees for J2 and so on. So basically whatever is inside the matrix is the cost that we, or the money that you have to spend if this person is given this job. Now the assumptions are we want to give only one job to one person. One person gets one job and one job goes to one person. We do not want a situation where this person gets J1 and J2, or J1 could go to 2, 3 etc. etc. We do not want. We want to give one job to one person. So the problem is to allocate or assign the jobs to people, under the condition that one job goes to only one person and one person gets only one job and the total cost is minimized. Now such a problem is called the assignment problem. Now what are the decision variables? Now each one job goes to one person and one person gets only one job. So xij equal to 1 if job I goes to person j. So if job I goes to person j. Now sigma xij equal to 1 for every I summed over j. So j1 for every I equal to 1 summed over j means this job goes to only one person. Now this for every job summed over people, now this person gets only one job. When I sum it over I, this person gets only one job, other one would mean this job goes to only one person. I want to minimize double sigma Cij Xij, which is the total cost of allocation, and my Xij is clearly a 0 1 variable, which means Xij is 1 if job I goes to person j, equal to 0 otherwise. Now Xij does not take any other value other than 1 or 0. Now this problem is called the standard assignment problem, and it is also a minimization problem, and it is formulated this way. Now let us look at some aspects of the assignment problem. Now the first aspect of this is, now this problem looks like a transportation problem. The objective function is similar, the constraints are similar, except that I have different numbers here. I had a ai and a bj for a transportation problem. Remember, the assignment problem is normally a square matrix. We have an equal number of jobs and equal number of people, whereas in a transportation problem we had m supply points and n destination points. So first thing is, the assignment problem is a special case of a transportation problem where m is equal to n. The number of supplies, you can always think of this as supplies and this as demands, or this as supplies and this as demands. So you could think of the assignment problem as a special case of a transportation problem with m equal to n and with all ai equal to bj equal to 1. It is like one unit is available in each one of the supply points, and that one unit is to be transported to each one of the demand points, and what is the cheapest way to do it. So the assignment problem is a special case of a transportation problem with m equal to n. Every one of the supplies ai equal to bj equal to 1. So xij greater than equal to 0 will become xij equal to 0 1. Now can we solve the assignment problem as a transportation problem because it is a special case, or do we need other algorithms to solve it? The answer is, what happens if to the assignment? Now let us take this. Now a feasible solution would be to give, for example, if I give this to person 1, this to person 2, this to person 3, this to person 4, I get a feasible solution. It may not be the best solution, it may not be the optimal solution, but it is a feasible solution. x11 equal to 1, x22 equal to 1, x33 equal to 1, x44 equal to 1 is feasible. x12 equal to 1, x24 equal to 1, x33 equal to 1, x41 equal to 1 is feasible. The point I am trying to convey is, every feasible solution has exactly 4 allocations. Exactly 4 allocations, 1 per row and 1 per column. So the assignment problem has, if we are looking at a n by n jobs are available and n people are available, we have n square variables or n square decision variables. We have 2n constraints, n for this and n for this, but the optimum solution or every feasible solution has only n allocations at the optimum or for every feasible solution. So which means if we have 2n constraints, then we need 2n basic variables, out of which there are only n allocations, which means out of the 2n basic variables, n basic variables take value 1 at the optimum, and there are another n basic variables which take value 0 at the optimum. So the assignment problem is a very degenerate transportation problem. It is a degenerate. If this were a transportation problem, then we would have 2n minus 1 allocations, because transportation problem has m plus n minus 1 allocations. Now out of these 2n minus 1 allocations, n allocations have value 1 and the remaining n minus 1 allocations have value 0. So it is a very degenerate transportation problem, and any degenerate transportation problem is not nice, it's not very comfortable to solve, because it would have too many intermediate iterations without reducing the objective function. So we do not solve the assignment problem directly using the transportation algorithm. So we need special algorithms to solve the assignment problem. So let us also look at some aspects of solving the assignment problem. Now let us look at the first condition for this. The first condition would be theCij's are greater than or equal to 0. It is a very reasonable assumption to have theCij's greater than or equal to 0, because if some people are going to do some jobs, they are going to charge some money. We are not going to have negativeCij's. So whenCij's are greater than or equal to 0, a very simple result would mean that if I have a feasible solution, with z equal to 0, then it is optimal. Then it is optimal, because we haveCij's greater than or equal to 0. So if we have a feasible solution with z equal to 0, that solution is optimal is a very intuitive result, becauseCij's are greater than or equal to 0. Now let us look at something. Now let us look at the first row of this. Now this job has to go to one of these people. Now if all of them increase their rate by say 1 rupee, and they make it 6, 10, 4 and 7 respectively, the decision will not change, because all of them have uniformly increased it by 1 rupee. So the solution will not change, the objective function value alone will change. Similarly, if all of them reduce their charge by 1 rupee, the solution does not change, only the objective function will change. So what we try to do is, we try to create as many zeros in this matrix, because we want a feasible solution with z equal to 0. So we assume that each one can reduce by a certain quantity till the first one becomes 0. The solution does not change, only the objective function changes. So subtract the row minimum from every row, so that the solution does not change, the objective function value alone changes. So we do that, and we get this row, subtract the row minimum, which is 3, to get 2, 7, 2, 6, 0, 3. Here the row minimum is 2, so you get 6, 5, 6, 0. Row minimum is 6, 0, 4, 6, 1. Row minimum is 3, 0, 7, 5 and 3. Now let us go back and do this for the column minimum. Now once again, this person anyway should get one job. So if this person uniformly increases his rate by 1 rupee for each one of these jobs, the solution again will not change, only the value of the objective function will change. Similarly, if this person decreases it by 1 rupee, once again the solution will not change. So we can do column subtraction, subtract the column minimum from every column and try to generate as many zeros as we can. Now already this matrix has been reduced to this matrix. So we take this matrix and do column minimum subtraction. This is the only column which does not have a 0. So once again subtract the column minimum to get 2, 1, so we had 4 here, we had 5 here. So this this we had subtract the column minimum to get 0, 1, 0 and 6. So, you get 0, 1, 0 and 6. Now, from this matrix we have converted it into a new matrix with every row and every column taking 0 value. Now, whether we solve this or whether we solve this, the solution will be the same. This has many zeros, we try to get a feasible solution from this matrix with z equal to 0, then it will be optimal. Now, we will see how we get the feasible solution. To get a feasible solution with 0 cost from this matrix, we will see much later. So, right now we have just defined the assignment problem and we have understood that a feasible solution with z equal to 0 is optimal. We have converted this to a matrix with zeros. We will get the optimal solution for this in the next lecture that we meet.